Żak. He graduated from Jagiellonian University in 2014, and he did PhD at UCL in London, which he finished in 2017. And after this, he moved to Queen's University, Kingston, Colorado, where he's now finishing his postdoc. And then after the postdoc, he will move to Germany. Today he will give us a talk about high accuracy rotational vibrational-electronic motion calculation.
Great, thank you, Adam. Thank you for having me today, and thank you for turning up in such a number. So today I'd like to say a few words about rotational vibrational electronic calculations for small molecules. So to share some knowledge from molecular physics and also share some news. So what has been happening recently. So brief outline. First, I'm going to talk very, very shortly about motivation, why we do it. So about nuclear motion calculations for astrophysics and Earth atmospheric science. Then I'm going to switch to something that's called curse of dimensionality. It doesn't apply only to molecular physics, it's in many areas of physics. And lastly, I'm going to say a few words very briefly about quantum dynamics of chiral molecules, so where we can use all this methodology we are developing. Okay, but let's talk about exoplanets first. What is an exoplanet? An exoplanet, as simple as it sounds, is a planet outside our own solar system. And there has been a famous example of an exoplanet or exoplanetary system discovered like a year ago, maybe 2 years ago. It's called TRAPPIST. And there are like 7 planets orbiting a star a few light years away from us. And 4 of these planets are potentially habitable, so there can be life. So it's pretty exciting. So it's a hot science nowadays. And the first detection of an exoplanet has been done very recently, like in 1995. So it's a very fresh science by these 2 chaps. And how they did it, they used something called radial velocity method. So when you have a star and you have a planet orbiting the star, the planet wobbles and the star wobbles a bit. It's a 2-body system orbiting around its center of mass. So, and we can detect the light from the star. So when the light from the star comes to Earth and we detect it, and the star is moving away from us, the light gets redshifted. And when the star is moving towards us, the light gets blue shifted. And we know that the star emits lines from helium, hydrogen, and so on. So what we observe is shift of spectral lines, emission spectral lines from the star. And if it happens on a regular basis, periodically, then it's a chance that there's a planet orbiting a star. So this is how they did it for the first time. And since then, since 1995, there has been a revolution in exoplanetary science. Until today, it's like about 5,000 planets detected, maybe more, I don't know. The numbers are being updated every day. So this diagram shows you how many planets we have. Every dot on this diagram is a planet outside our own solar system. And as you can probably see, the easiest planets to detect are the big ones, this is size, and planets that are close to the host star. And we have Earth, Venus, and other planets in the solar system. There are planets here, but they are very difficult to detect. And there will be like this James Webb telescope due to send in 2021 if everything works fine. So it's a very dynamic field and very exciting. So, so we know our Jupiter. It's pretty far away from the sun. Yes, so it's a planet that mimics Jupiter. It's like it has the same or similar composition to Jupiter. So from the orbiting, the velocity method, we know what's the mass of the planet, what's the radius of. Yes, we can. This is another story, and I'm going to tell you about it in like a few minutes' time. Yes, so it's very interesting. the temperature of the planet. Right. Yes, the average temperature of the planet or the atmosphere. Yeah, yeah. So some people are trying to predict weather on other planets. So it has gone to so far. So there are a few questions to answer. Like the first question is like, what are they made of? These planets, how did they form? Exactly. Yeah, but what type of cosmic dust? But we can go even further than that. Was the weather like there? And eventually, we come to the ultimate question that's important not only like for physics, but for human race. Are they habitable? And is there life on the other planets? This is a grand question to answer. I could talk about it for ages, and I'd be so glad to talk about it with you after the talk, because it's a very exciting topic. Like, it doesn't have to be based on DNA that we know. There has been a recent paper with 8 per basis DNA. We have 4. So, you know, it's a slick topic. Okay, so these are the questions that people are trying to answer nowadays. And the main source of information is something that's called transit. When a planet passes in front of a star, we can see that the star dims a bit. So, oh, come on. So if you see the planet coming in front of a star, you can see that the brightness of the star goes down a bit. It gets dimmer. In other words, we observe a dip in the brightness curve of the star. And if this dip shows up regularly, like every few days, it's a sign that there might be a planet orbiting the star. Okay? And not only that, but we also know that planets usually have some atmosphere. And if we have a star and the starlight passes through this atmosphere, then we know that some molecules in this atmosphere can absorb light. And we know the spectrum of the star because we can measure it. And if the planet goes in front of a star, there can be some extra absorption lines in the spectrum that we can pick up and try to figure out what molecules cause this absorption. So it's a fingerprint that we can detect from Earth. Like in here, you have a star, you have a planet, you have a light passing through the atmosphere, and we have a telescope, and it measures the light coming from the star. And what we actually measure is a spectrum. So it's absorption intensity as a function of wavelength. So here's an example spectrum of methane. What range of electromagnetic spectrum are we interested in? Particularly microwave to the UV. Why? Because molecules, sometimes they absorb microwave light and light radiation, and they start rotating. So microwaves usually induce excitations in rotational levels of molecules. Infrared light is vibrations of molecules. So like in here, if a molecule absorbs infrared light, it usually starts to vibrate. And in the UV, sometimes the UV light can excite electrons inside the molecules. So these are the 3 regions that we are interested in. And luckily, molecules obey the laws of quantum mechanics. So we can try to figure out beforehand what the spectrum of a molecule will look like and try to compare it with a measured spectrum from the exoplanet. So what we are really interested in are the rotational vibrational energy levels of molecules, because these levels and transition between these levels are responsible for absorption in the atmospheres. And that's how we can tell about, you know, weather and life and all these interesting things. There is a hype on this. So very briefly, just to wrap up like what's going on, we have some molecule which has vibrational state and some rotational states, and this molecule, you know, the molecules occupy these states. They are quantum states, so they occupy these states. And we can observe some transitions between these states. So we can have many, many transitions between these states. And what we really observe is some absorption intensity as a function of wavelength, so as a function of the separation between states. And we have different types of motion inside of molecules. We have vibrational motions, rotational motions, some couplings between vibrations and rotations, like when you have two people on a disco and they go around, there's a centrifugal force, right? So this the same happens to molecules. And we have some electronic energy associated with it. And the intensity, so the absorption intensity, is proportional to the square modulus of the transition dipole moment. So what we are really interested in are the energy levels and wave functions of the molecule. So this is the focus. Okay. And to give you an example why it's really important to have these quantum mechanical models, let's focus on planet 189733b, which is 63 light years away from us, is very hot. And in 2007, people measured just 3 points, a spectrum for this planet, for 3 different wavelengths. It's not really impressive spectrum, is it? Because look at the error bars. So this is a wavelength. It's huge. These were the early days of so-called transit or exoplanet spectroscopy. But what people did from my group from London, they fitted a model for water molecule. Amazing, isn't it? And they published Nature paper on that. It's a water feature, isn't it? Just 3 points. I had the same reaction. So a year later, there has been some extra measurements of many more points. These are the old points, and they fit it perfectly. They match. There's not a chance that it's not water. So it's first detection of water on other planets, and you couldn't do it without quantum mechanics behind it. So, you know, the question is, why do we really need theory? There was one of the answers was that. The other answer is completeness. What do I mean by that? Let's have a look at this spectrum. This is a spectrum recorded by a telescope, I don't know, Spitzer or some other guy. It's a spectrum of a brown dwarf. It's a cold star, I think. And this is wavelength, this is absorption. And the observed spectrum is the white one. And people have tried to fit a model which is purely empirical. So they measured something in a lab, they extracted single lines, and they tried to fit the spectrum, and it doesn't match very nicely. It's pretty bad, I would say. So what people from our group, Sergei Yurchenko, did, they fitted a fully quantum mechanical model to it, high accuracy model. And this is what they got. First principles, no fitting, no things like that. Why is that? Why the match is great. Why does it happen? And the answer is completeness. This model had 10 to the power of 10 lines, or 10 billion lines, absorption lines. You have to include almost all the lines to account for the background. They all add up to small features in here. And it's almost impossible to get all the 10 billion lines from experiment. It's such a tedious work to do. So theory comes to rescue when it comes to very, very many lines. So there's a database called Hydron, which stores spectra for molecules, and for high temperature spectrum of methane, it stores about 250,000 lines. Our line list, so our spectrum, has 10 billion lines, so it covers all the spectral regions which are inaccessible to experiments sometimes, due to laser limitations, things like that. And it also has very high accuracy. So another example, we have hydrogen peroxide. This is the blue ones are all the experiments. The red one is first principles. And all these lines are really, really accurate, but it's, you know, they all merge together into such a blurry thing. Also poisonous things, so HCN, it's pretty hard to work with it in the lab, I think. I wouldn't dare to do it. So there are only a few vibrational bands really measured really accurately in the lab. And theory can do it safely, right? And why it's important? Because people have postulated that HCN might be present on planet 55 Can3e, and it has been detected. only because we had the model somewhere around here, and the experiments were unavailable. So this is one of the reasons why we need theory. High temperature spectra, and something that's hard to measure. So if you have 1500 Kelvin, and you have a chamber in the lab, it tends to burn down. There's Peter Bernath in the US is doing these high temperature experiments. He says like graphite just burns down. There's no material to do these spectra sometimes. And theory is pretty safe and clean. And the last example and the last reason why we use, from my perspective, why we use theory is high accuracy reference spectra for atmospheric science. So there's all this hype about greenhouse effect and global warming. And to measure accurately the concentrations of CO2, methane, water, and other molecules in the Earth atmosphere, we need to have very accurate reference spectra. So, for example, this is a spectrum that we calculated. These are all rotational lines. And what we are really interested in are absorption intensities, because you compare these intensities and you can retrieve concentrations. So how it's done, we have a satellite, it's called OCO2. I mean, NASA has it. And there's sunlight passing through the Earth atmosphere and bounces back and goes to the satellite, and CO2 absorbs some light. But we need to have some reference line intensity to get concentration out of it. And so what you can do, you can build a map, dynamic map of concentration of CO2 on Earth. And as you can probably see, most of CO2 is concentrated in the upper hemisphere, so the northern hemisphere. And I think there's a good reason why it's that, because in the southern hemisphere there's like oceans, and most of cities are in the upper atmosphere, northern hemisphere. So, in order to get such a map, what we need is very high accuracy intensities, and experiment struggles with transition intensities. It's very hard to measure transition intensity down to 1% of accuracy. And so if you want to get 1 ppm resolution on this map of concentration of CO2, you need about 0.3 to 0.5% of accuracy in line intensities. And so part of my PhD was to compute such intensities. And just, I can talk about it maybe later, but we kind of shifted the way towards ab initio calculations from experiment. So we showed that our ab initio calculations are actually more accurate than most of the experiments, okay? It's a very, very delicate statement. It's not more accurate than experiment, but it's more accurate than experiment that can cover a lot of lines. So this has been used to monitor the CO2 concentration. So accurate transition intensities. So now you know why, and I know why now, why we need theory. We did it in London. This is a lovely campus. You can drink beer there, and it's all fine, it's barbecues. And this is my former group, led by Jonathan Tennyson. It's called the ExoMol team. And yeah, here are the people. And believe me or not, but every person in the group has a molecule assigned. And it takes about a PhD lifetime to compute a high accuracy spectrum for a molecule. It's so much work to do, so that's why there's a molecule person association, 1-to-1, sometimes 1-to-2. Okay, methodology, how we do it. We know why, now how. To start with, let's write down the Hamiltonian. We write down the Hamiltonian for the molecule. We have kinetic energy operator of the nuclei, and we have vibrational coordinates for the molecule, we have rotational coordinates for the molecule, and we have electronic Hamiltonian, so all the electronic energy and all the interactions between nuclei and electrons and so on. But if you take a closer look at this nuclear Hamiltonian, you can see that's inversely proportional to the mass of the nuclei. And the nuclei are much heavier than electrons, about 2,000 times. So from the perspective of an electron, nuclei are almost stationary. And this is the basis for the so-called Born-Oppenheimer approximation. So for the moment, what we can do, we can set this t to 0 and solve the problem for electrons only. So solve the time-independent Schrodinger equation. What we get from it is a wave function for the electrons for a given configurations of nuclei. And the corresponding energy is called the potential energy surface or electronic potential energy. And we solve this Schrodinger equation for many, many configurations of nuclei, stationary, clamped nuclei. And then we can expand the total molecular wave function in this basis that we just calculated. And I goes over so-called electronic states. And what's the basis for Born-Oppenheimer approximation? That we say different electronic states, so different phi i's, are independent. They are decoupled. So our total wave function is a product of the nuclear wave function and the electronic wave function. And if we do the maths, we arrive at a pretty simple equation for the nuclear wave function. So vibrations and rotations. And we have such an equation for every electronic state. So to put it into pictures, I like pictures rather than formulas. So this is the equation, and we can solve it for the first electronic state. So this is the curve, the continuous curve, which is fitted to. So we solve the electronic Schrodinger equation for many, many configurations of nuclei, and we get this curve, and this serves as a potential for this equation here. And what we get out of it is vibrational energy levels, rotational energy levels, and that's what we want to get. So the methodology is as such. We start off with electronic structure calculations. There are many programs to do this. We solve the Schrodinger equation for many configurations of nuclei. We get potential energy surface called PES, but also dipole moment of the molecule depends on the geometry of the of the molecule. It's called dipole moment surface, and we feed in this PES into a program to solve the row vibrational Schrodinger equation, and we get energy levels and wave functions. If we combine wave functions with the MS, we get line intensities, this transition dipole moment. And energy levels combined with line intensities is a spectrum. We call it a line list. So this is the procedure. Okay, so there are a few key elements to do this type of calculations. We need to choose a basis for rotations and vibrations. We need to define a coordinate system for the molecule, like in here. So imagine you have a SO2 molecule, triatomic, and we have to attach a coordinate frame to it. We define some internal coordinates to account for vibrational motion. And that's it. And we just write down the Hamiltonian and run it. So how it's done? We expand the rotational vibrational wave function as sum of products of rotational functions and vibrational functions. But luckily, we know that rotations in 3D space are pretty simple. I mean, we know some analytic solutions to symmetric top model system. So we can use the basis of symmetric top with J, so the total angular momentum, as a good quantum number. And we can just take the Hamiltonian, the total Hamiltonian, and integrate out over all rotational coordinates, so all the angles. These are the Euler angles here, so alpha, beta, and gamma. And what we get is a Hamiltonian that's labeled by J, which is a good quantum number, the total angular momentum, and some K's, which is the projection of the total angular momentum on Z axis, which is molecule fixed. And so we have the vibrational problem. So we need also a basis for for vibrations. We expand the basis, and I like to think about this in such a way that if we have a small basis, our picture of the molecule is pretty bad. It's pretty harsh. But if we build a bigger basis, the picture becomes clearer and better, and eventually we get a very nice picture of our solution, like Lego blocks. So that's how we construct our solutions. The bigger the basis, the bigger the n, the better the solution is. So we chose our basis for vibrations, for rotations. And then what we get in the end is a matrix representation of the Hamiltonian, as in typical variational calculations. And the task is to diagonalize this matrix. What's nice about this is that J, the total angular momentum, is a good quantum number. So we can solve the Schrodinger equation for every J separately. And this is pretty nice. So we like to go into very high J's. I did like J150 or something. It becomes pretty big. So to wrap up, from solving this equation, so this matrix, from diagonalizing this matrix, we get eigenvalues, which is basically energy levels, which is basically line positions. We get wave functions, which are used to compute line intensities. We can add on top of it some line shapes, because every line has some width. And we can add some quantum numbers. And this is how a spectrum looks like. There are few databases that store spectra for many molecules. There's Hydron database, and there's also our London database. Okay, how to do it in practice? It's easy to talk about theory, but if you want to do it yourself, there are a few computer codes available to compute high accuracy spectra. For diatomics, there's a code called DUO for fully rovibronic Schrodinger equation. For triatomics that I've been working on there's a program called DVR3D by Jonathan Tennyson. For 4 atoms, 5 atoms, there's a program called Trove by Sergei Yurchenko. There's also a program called Genius. So many other programs, and also a whole class of methods called MCTDH, or multi-configuration time-dependent hard-tree methods. So there's a bunch of codes available. But what all these codes have in common is that they can't go beyond 5 atoms, 6 atoms maybe. And why is that? So you can only do very small molecules. Why is that? So imagine you have a diatomic molecule. There's only 1 degree of freedom, internal stretching. The basis is just 1 dimensional, 1 index. It goes from 1 to n. But if you have more dimensions in your problem, then the basis typically is a product of single particle functions, or and every of this function has, each of these functions have an index which can go freely from 1 to n. So the total size of the wave function is n to the power of d, where d is number of dimensions. So in 3D, you can think about it as a cube, and every block in this cube is a basis function. And the number of dimensions is 3n minus 6. So to give you a picture of it, some intuition, if you have a water molecule and you use only 10 basis functions per dimension, the memory requirement to store such a wave function is pretty small. For 4 atoms, it's also fine. But when you move into 6 atoms, things start to become pretty bad. To store 1 wave function for a 6-atom molecule, you need 8 terabytes. And 8 terabytes is ridiculous. It's a horrendous number. You can't store it. It's hard to store. So imagine you want to do 9-atom molecule, or a problem in your area, which is 21 dimensional, because 3 times 9 minus 6 is 21. So why do we even care about such a molecule? This molecule is called dimethyl sulfide, and it's considered a biosignature. So if it's detected on other planets, exoplanets, it's almost a certain hit for life. And it's Nobel Prize for people who detect it, basically. I hope so. So we collaborated with MIT on measuring and producing a high accuracy spectrum for this. But the problem is, if you want to store 1 wave function for this molecule, it's about 10 to the power 11 gigabytes, which is totally bonkers. Like you can't go around it. So why do we keep all the basis functions? How about only selecting the basis functions that are really important for our solution? So, for example, you constrain the indices of the individual basis functions so that the sum of the indices is smaller than some truncation parameter. And then, if you use such condition, the size of the basis, so n to the power of d, reduces down to binomial scaling. And for this molecule, we can get down to 300 megabytes per wave function, which is already tractable. So this whole problem is called the curse of dimensionality.
Yeah.
Yes, you can do. So there's no one recipe for that. Exactly, exactly. So my dream is to develop machine learning thing to pick the best basis functions, and if you add one basis function, how the energy will change. But if you add two basis functions and how they correlate together, if they add it in a pair or triple. So what's usually done is so high energy basis states are usually less important than low energy basis states. And this condition basically reflects that sometimes. You can weight it with some frequencies and so on. So you can think about this whole procedure of pruning the basis as going from a cube into a tetrahedron. And all this reduction in memory manifests itself even more in higher dimensions. We go from hypercubes to so-called simplexes, and the savings is huge in higher dimensions. So this is what I've been working on for the past year and a half. And just to give you a brief recap of how we approached this problem, we are interested in solving the time-independent Schrodinger equation. There's for the nuclei and so on. What people usually do, they expand the wave function as a linear combination of some basis functions. And then they put this wave function into the Schrodinger equation and multiply from the left by another basis function. And this is the classic variational approach, where we get a matrix representation of the Hamiltonian, the overlap integral, and we have HU equals SUE. So this is undergrad knowledge. And this is called variational Galerkin method. There's also another class of methods, a bit less known. Instead of multiplying from the left by the basis function, how about multiplying from the left by an eigenstate of the position operator, which is delta function? And what happens then is that we solve the Schrodinger equation at points, at discrete points, and we interpolate the solution in between. So as you can see, this is very similar eigenvalue problem to this one, but instead of overlap matrix, you have just the values, by definition, but just the values of the basis function at a point. And there's no integrals. There are no integrals at all in this approach, because the delta function just kills all the integrals. Here, it's quite hard to do sometimes when you have many dimensions, because you need quadratures, and it's hard to get integrals. So we proposed a method, a collocation method. This is called Collocation Approach, this at points, in which the memory cost scales as binomial factor or even better. So the work was done with Tucker Carrington, chemistry department from Queen's University. It's in Kingston, Ontario. Kingston is halfway between Toronto and Montreal, on the border with New York State. It's a lovely town, but I don't like it. You know, and in a standard approach, in a standard collocation approach, this is the working equation. This is the equation that I showed you before, but this is the one, but in more detail. We have b double prime, which is just a second derivative of the basis function taken at a grid point. We have v diagonal, which is just the value of the PES, or potential energy surface, at a point. And we have b, which is just the value of the basis function at a point. It's called the collocation matrix. But you know, it's a generalized eigenvalue problem. There's something on the right-hand side. We would like to have something simpler than that. So after some tricks, and the trick is very simple, but it's more behind it. What you can do, you can just replace b times u with some z, like here. And what you're left with is a regular eigenvalue problem with b to the minus 1 here. So this is a simple transition from this equation. And I'd like to put your attention to it. There's no integrals here. There are no quadratures, nothing like that. So this is the equation we're working on. It's a regular eigenvalue problem. It's a real Hamiltonian. It has a diagonal potential energy surface. No matter how complicated the potential energy surface is, you can just put it in and just you need it at points. And there are no integrals, which is nice. And you can use it with any type of kinetic energy operator. You because you only need to know the value of the KEO at points. And we use this equation with non-direct product basis, so this pruned basis, and also non-direct product grids. And to get eigenvalues from such a thing, you can do either direct diagonalization or something called iterative diagonalization, or you can use iterative eigensolver. It's not diagonalization. So in order to get eigenvalues from iterative eigensolvers, you need to code matrix vector products with the Hamiltonian. And this can be done very efficiently with the method I'm proposing. So, okay, just to speed up, we need to choose a multidimensional basis set and a grid. The basis set is a product of basis functions, but the indices will be constrained. So the indices, they don't go freely from 1 to n, but the sum of the indices is smaller than some factor b. And you can also use some function of these indices to, to get a better basis. And what are the basis functions here? So what are the one-dimensional basis functions? And this is really the key of all this stuff. It might be used also in other areas of physics, and it's a new basis. And I think it might save a lot of like memory and things like that. So we call it a hierarchical basis. And a hierarchical basis is just a linear combination of any functions you wish. So you pick up some primitive basis functions, like harmonic oscillator basis functions here. And you define a new basis through a linear combination of these functions. And how is the hierarchical basis defined? Well, we require that the hierarchical basis is 0 at grid points with indices smaller than the index of the basis function. So that the A matrix, the transformation matrix, is lower triangular. This is a lower triangular matrix. Okay, let me put it into English, okay, because pictures are better than the equations. So we have a column of basis functions called hierarchical basis functions. On the right-hand side, we have harmonic functions. This is the transformation matrix. And the first hierarchical basis function is just proportional to the harmonic basis function, which is Gaussian. This is Gaussian. The second hierarchical basis function has 0 at the first grid point. The third hierarchical basis function has a node at the first grid point and the second grid point. The fourth hierarchical basis function has a node or 0 at the first, second, and third grid point, and so on and so forth. Okay? So for example, the 21st hierarchical basis function will have zeros at all 21st grid points for any grid you choose. So it's a flexible procedure. And you can use the fact that it's 0 to kill some elements in your matrix vector products. And it's a linear combination. They span the same space. It's pretty nice. Okay, we also need to choose a grid. I just want to very briefly say that we use something called nested grids, where nested grid is that a grid with n points is fully contained in a grid with n plus 1 points, nested. And okay, that's how a nested grid point, that's the grid that we're using, that's how it looks like. It's called layer grid, and it's something called sparse grid, but I don't want to go much about it. Okay, so in many dimensions, so the equation I showed you before was in 1 dimension, but now we have many dimensions, and our Hamiltonian looks like this. We have B inverse. This is the inverse of the collocation matrix, and we have this something like tensor product. But because we are using a non-direct product basis, we select only some functions. Our Hilbert space is not a tensor product of individual Hilbert spaces. So this is not a real tensor product. But because we use the hierarchical basis, we can retain the properties of the tensor product, which is pretty nice. And this Hamiltonian, as you can probably see, is non-symmetric. So we need to use something called Arnoldi algorithm to get eigenvalues and eigenvectors from it. It's encoded in ARPAC library, and this is what we use to get energy levels from it. In order to do it, you need to code matrix vector products with it, okay? Okay. Come on. I will save you from the technical details of it, but what I want to point, maybe this one is better. What I want to point out is when you do a matrix vector product, this is your vector. This is a vector labeled by D indices because it's D-dimensional space. This is your matrix, which can be done sequentially. And this is the output vector. If you have direct product basis, you have these cubes, you can transform this vector into the next one, and next one, next one, next one, and they all have the same size. But these cubes are huge. This is what we want to avoid. And if you prune your basis, but you use a non-hierarchical basis, you start with a vector which is of size of a tetrahedron. But in the middle here, you'll get something bigger. And you have a transformation between spaces of different sizes. And you can't do the inverse unless you do pseudo-inverse, which is totally nonsense in here. So hierarchical basis conserves the volume in the transformation space. This is what I wanted to point out. Okay, some results. 5 more slides with results. So we tested the method with this hierarchical basis, this whole Hamiltonian, on a very dummy molecule. SO2 is a simple one. We used normal modes. This is a simple harmonic kinetic energy operator from the nuclei, for the vibrations of the nuclei. We used quartic force field, so potential energy surface expanded in 4th order in displacement. And we got energy levels, vibrational energy levels for different sizes of the basis. And you know, if you increase your truncation parameter, the convergence, so the energy levels, they don't change much, so the method works perfectly. So we used hierarchical basis. These are pruning conditions. We choose this alpha based on some frequencies of the normal modes. But this is simple. How about doing a bigger molecule, 5 atoms? So it's 9 dimensions. And I want to point out, if you have a problem in your area, which is multidimensional and it's coupled, phonons, whatever, qubits, if it's 9 dimensions and whatever problem you have, you can use this method. It's general, it's not restricted to molecules. So again, we used harmonic KEO, quartic force field, although you can use any type of potential energy surface you wish. And we started off with harmonic basis, then we constructed hierarchical basis. We used a bit more sophisticated pruning condition, which accounts for the fact that if you have a many-body system, it's quite rare that you have many degrees of freedom coupled strongly together. So for example, it's quite common that you have 2 degrees of freedom coupled, 3, maybe 4, but not 9, like very strongly coupled. So this basis reflects that. It weighs less, this multi-coupling basis functions. And here are the results. So these are vibrational energy levels for different basis set sizes. The B parameter controls that. And the differences between the levels are sub-wave number, which is, you know, we don't have to worry about a bit better than that. We also compared it to another method by Tucker-Carrington, which is more complicated. It all agrees well. The method works. So, 5, 6, I would say like 7 digits. So my eigensolver, the tolerance parameter was 10 to minus 8, I think. I think 7 significant digits, but you could do a bit better. I mean, so what's nice about this, we can get many energy levels. So if you are only interested in the ground state or maybe a few levels, you can get pretty good accuracy, precision. But I would say 6 is safe. 5, 6, 7. The precision goes down. Yes, yes, but it's non-variational. So we don't have. Okay, so we didn't aim at comparing with experiment because this potential here, we know the convergence properties. So we know that if we increase the basis size, the energy levels, they don't change much. So it's the accuracy of the method, not the potential. So for a given potential, we know that the method will converge pretty nicely. There are some experiments, yes. They are not so accurate to this level. Yes. So there are experiments, yes, and it wasn't the point to compare with experiment because the accuracy of the method, of the calculation is the accuracy of the method and the accuracy of the potential energy surface. And this potential was from 1997. We will. Yes. 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 So yeah, so if we use a better potential, we can try to compare to experiment. So our agreement to experiment would be like 2 wave numbers here, maybe 5 wave numbers, maybe 10 wave numbers. It all depends on the accuracy of the potential. So I did similar calculations for, okay, SO2. I did calculations with a different method, with a very accurate potential, and we can compare this to experiment. But this is only a test if the method works. Because the method works if we extend the basis and the energy levels, they don't change much. This is the stability of the method. But then we have this accuracy, what you mentioned, yes, relative to the experiment. So, you know, if someone comes up with a potential, it's fine. It's electronic structure. We develop a method that somehow circumvents this curse of dimensionality, but only slightly. We use non-direct product basis set and non-direct product grids, and hundreds of energy levels can be computed cheaply for 5 atom molecules, 6, 7, maybe 8 sometimes. So we can do a bit bigger than that. So the code is available now. It's fully parallelized. It's done on high-performance computing systems. And just 2 slides of why do we even do this? Like, okay, comparing to experiment, but where further we can use it. And we can solve the time-independent Schrodinger equation and use these solutions as a basis for time-dependent Schrodinger equation to model dynamics of molecules in electromagnetic fields. Like, for example, optical centrifuge on molecules where you excite the molecule to very high rotational states. Alignment of molecules. To model this, you need to solve time-independent Schrodinger equation with the methods I've described. And then you put it into time-dependent Schrodinger equation and propagate the wave function in time. And the last slide, the project I'll be working on, is something called superchiral optical centrifuge for chiral molecules. Chiral molecules are molecules that have at least 2 forms. And these 2 forms, the mirror images of these forms, they don't overlap, like our hand. And a long-lasting question was, can we separate the enantiomers, the 2 forms? And, you know, pharmaceutical industry is huge money into it. Can we do it cheaply? And yes, people have done it recently. They've separated enantiomers using lasers and some electric guides. But I wanted to go a bit further than that and ask, can we transmute or transform one enantiomer into another one without breaking bonds, using quantum tunneling or quantum mechanical processes? And I think this can be achieved through a new form of light, pretty new, called superchiral light. You apply this superchiral light into something called optical centrifuge, and you excite the molecules into very high rotational states. They are very highly very quickly rotating. Like in here, you climb the ladder of states, and because the light is chiral itself, a chiral object interacts with another chiral object selectively. And we can discriminate the populations of left-handed and right-handed enantiomers. And at the very end, we can just transfer the population from one well into another. So starting from 50-50 mixture, we can get some enrichment of one enantiomer. And this is what the pharmaceutical industry in long term would love to have. So we collaborate with, I mean, that's what I'm going to be doing in controlled molecular imaging group. Exactly. So this is what I'm going to do in DAISY in Hamburg. They could assassinate me, yes. Yes, but it's a far-fetched thing. So it's, you know, we start off with very simple molecules, like 4 atoms, like in here. and hydrogen thioperoxide. In order to move, not yet, but this is the first step. Yeah, yeah, exactly. So Daisy, Aarhus University, this is our collaboration. They set up an experiment to do this, and I'll be doing some calculations. So if you're interested, I'm happy to talk. Thank you very much for your attention. Thank you.
Okay, questions?
I have a question about this chiral light. In terms of the solutions of Maxwell equations, what are these? Bessel beams or what?
It's somewhat like Bessel beams, but so we have circularly polarized light, right? And it's a form.
But circular polarization is
different.
a very general property. It could be a plane wave circularly polarized. Bessel beams are also.
So the standard circularly polarized light, when we have the polarization vector rotating at some frequency.
That's
It's
circular polarization.
Yes, that's circular. It's a form of superchiral light. It's the simplest form. Superchiral light, in principle, is when your polarization just rotates very quickly at a very small distance, at a molecular distance.
So
You can do it.
In terms of Maxwell equations,
It's a new solution.
What do you mean new solution?
It's a solution of the form of circularly polarized light.
But there are Laguerre-Gauss beams, there are Bessel beams. Which
It carries angular momentum somehow.
Of course,
Yeah.
Bessel beams carry,
Yeah.
Laguerre-Gauss beams carry. So how is it different from those beams that carry angular momentum that are?
I think it's so it's just another. It's no different from it. So I would say, this is the one. It's just another shape which maximizes the rotation of the vector. Where we are.
But do you use a certain particular solution of Maxwell equations?
Yes.
That can be written down.
I hope you can see it here. This is circularly polarized light. And okay. And superchiral light has very quick rotation around nodes, and that's it.
Quick means that omega is.
It gets bigger, yes, and it maximizes the interaction strength between the chiral discrimination factor.
No, but my question is, do you have a particular solution of Maxwell?
I haven't produced my solution, so it's just a project proposal. It's from science. So guys in 2012 did it. They solved Maxwell equations to get it, and there is something called the chirality property of light, which is maximized by this light. This is the condition for superchiral light. So chirality property for circularly polarized light is equal to 1. Everything bigger than 1 is superchiral light. And these are legit solutions to Maxwell equations. It's a scalar product. So this is a vector product, and this is a vector. So it's. Oh yeah, maybe. Yeah, yeah. So in some units, yeah, in units of some, yeah.
Okay, any other questions?
Yeah, I can send you the paper.
I have just a general comment that it's really a great work, particularly from the point of view of astrophysics, right? Because a few years ago I attended a ALMA conference, and they still had some, well, many unidentified lines, and I understand
species,
that the access to your database sort of helps to solve
yeah, so
the problem.
XOMO, yes.
And from the point of view of methodology, I see no problem in using theoretical models instead of laboratory, because in my research I deal with something as simple as just Fe2 emission in the optical band, pseudo-continuum, and still cross-sections are better when they are just taken as calculated instead of laboratory. There is no laboratory results for that.
I see, yes, so these are the regions where theory is really really important for, I agree, totally. Like, I think theory and experiment together is something qualitatively new and better than they exactly. So we can confirm. But as you said, there are so many lines in the ISM. So there are many molecules that can be formed. This carbon change and all. Yeah. So it's an ongoing thing. It's a hot topic now. Yeah. People have done it. People have done it. It looks weird, but they have measured. So you get like 2 pixels from the planet is just 2 pixels, but they could figure out temperature differences, seasonal temperature differences on the planet, and then they fitted a model that there are winds, and so there are some pictures of actual planets with some resolution, basically. So these are early days, but people try to predict weather on other planets. Yes. No, exactly. Not like on our TV thing, yeah.
Just a basic question on quantum chemistry. At which stage do you put in more juice, or like you have to sacrifice some data when you take into account singlet triplet transitions and conical singularities?
Mm-hmm. So it's a very good question. Most of the times in infrared, we are interested in the ground state, electronic ground state. But sometimes when you want to do UV spectra, you have to take into account spin-orbit coupling, yes, and vibronic coupling, so go beyond Born-Oppenheimer approximation. And we've done it in the past. So where is it? We did a spectrum for SO2 with 2 electronic states, and you just, you built a model, you solved the Schrodinger equation for the ground state, for the excited state, and you built a vibronic model to get raw vibronic energy levels from it. Yes, so it's a part of our project. But I didn't want to mention it much because time constraints, but yes, we do it.
I will ask the second part of my question in private when we will drink coffee and eat cookies,
no
but it has to do with scales. In a sense, from quantum field theory, I am accustomed to think about a situation where a quantum calculation extending over different scales requires different technology when the scale change. Mm-hmm. But my question now is very simple. Is your accuracy, in which sense is your accuracy uniform across the spectrum you are calculating?
Very good question. I missed it. Thank you. So, because we are using exact kinetic energy operator, we model rotational transitions exactly. And the only source of error is in the vibrational energy levels. And the accuracy of the vibrations depend on the accuracy of the potential energy surface, which is calculated from electronic structure programs. So we can claim in the program, the methods I've been working, that all rotational transitions and levels within a vibrational band are of the same accuracy. But the higher you go in vibrations, the worse it becomes because the basis size, the convergence. And unless there are some resonances, so when 2 energy levels are close together and you have to model your wave function very, very accurately, then sometimes the rotational transitions are also not very accurate. And these resonance interactions are really a real pain nowadays because they are very sensitive to minor inaccuracies in the potential energy surface. And we develop a method to assess it from the theoretical point of view as well. So to give an error bar, a theoretical error bar somehow on this thing. Yes. So the worst thing is electronic transitions. So when you get electronic ground state, your potential energy surface, and you want to compute this vertical excitation energy from first principles, it's very hard to do. So this is a huge error. then a smaller error is for vibrations, and almost non-error is for rotations because it's calculated from first principles from beginning to end. Yes, but so this is the overview of the errors.
Okay, anyone else? So I also have a question about this curse of dimensionality. So there are some different methods in physics which deal with this problem. For example, we have density functional theory and so on, which is it applicable here, or are there any people who try to use this kind of methods to solve this problem?
So, so I'm personally not a big fan of DFT because it's super accurate for molecules that it has been fitted to. So DFT uses some functionals which are empirical. And it does great for big molecules. We read papers about DFT calculations for 40 atom molecule or something. But it works fine whenever the functional, as long as it doesn't fail. And there are examples. There has been a paper which showed different functionals, and they gave like so inconsistent results. So it's a perfect method, but it has to be applied to a molecule that is within the range of applicability of it. So they're like this database of many molecules that produce a functional. So it's a way. So there's probably no other better way around. There's MCTDH class of methods, which is also a promising candidate. And we also work on something called rank reduction tensor block power method, which is an alternative to MCTDH. But, you know, so the world record for many-body system, molecular many-body system, from first principles, so not DFT, is 18 atoms. And Tucker Carrington, my supervisor, actually did it with rank reduction block power method. It took a month on the supercomputer, but they computed a spectrum for naphthalene, which is like totally crazy. It's so many molecules ahead. So people struggle with 6 atoms, 7 atoms, and he did like...
So I'm just asking because this density functional method is actually proven to be consistent mathematically, that if someone knows this, I don't know, God-given functional, then you can calculate everything.
Yeah, the question is, what is the functional? And I think there's a theorem that you can't find it like in a closed form or something. And this is a question... Yeah.
And
so
how many gods do you have?
This is a question of accuracy, yes.
Okay.
Yeah, so the method is consistent inside, but this is the question that you ask. How you relate this to experiment. So the method is consistent. This is what I showed for our method. But the accuracy of this method depends on the accuracy of the functional or the potential. So this is, there's a huge field of electronic structure theory, and so we just take from them and use it.
Thank you.
Thank you.
No other questions, so let's thank our speaker
thanks
again.